Welcome everyone. So today is the next edition of our IMSc Diamond Jubilee Distinguished Lectures, and it's a pleasure to have Professor Shailesh Chandrasekharan with us. So Shailesh actually did his undergrad in IIT Madras, which is our neighboring institute, and then he went to US for his PhD in Columbia University. So he did his PhD in Lattice QCD. But later he switched a little bit, though he's still a lattice gauge theorist, but he does more problems on the interface of high energy physics and condensed matter physics. So he actually develops algorithms for one of the most difficult problems in theoretical sciences, which has this sign problem, and he has a number of algorithms where he showed how to solve this sign problem in many myriad different scenarios, especially when you have fermions in the system. And recently he has been interested in how to solve problems in theoretical physics using the quantum computers, on which he will talk today. And apart from a brilliant researcher, he is also a very good mentor. So he actually visits India quite often. When we were students, he was visiting TIFR, and he gave an excellent series of lectures to us. And he was visiting ICTS a month back, where he also gave a series of lectures. And of course, to his laurels, he has the DOE Outstanding Investigator Award, and he was also elected the Fellow of American Physical Society in recognition of his outstanding work. So, Shailesh, please.
Well, thank you, Santan, for a kind remarks. And also thank you for inviting me, and I realized that Bhaskaran sort of initiated this whole thing. I would have loved to spend more time. Unfortunately, this is the end of my trip to India this time. After the pandemic, it has been quite exciting to visit many places, especially back home. So today I wanted to tell you about some research that I've been doing on trying to sort of again continue my efforts in solving strongly interacting quantum field theories. There's been a huge hype, I would say, that maybe someday, I don't know if I will still be alive, that there will be this new kind of computer called quantum computer, which will be able to solve all of our sort of hard sign problems. That's one of my favorite topics of research. And that then motivates us to think about quantum field theories in a different way. So all the motivation comes from that hype that maybe someday we will be able to have this computer, but then we'll have to reformulate or rethink the way we think about quantum field theories, especially things like QCD, which is really hard to solve today in many different ways. And that sort of motivates my research. So I should definitely thank some of my collaborators. My long-term collaborator has been Uwe Jens Wiese. He was my mentor when I did my postdoc at MIT long ago. That is when we actually started thinking a bit about what I'm going to talk today. We actually proposed some different ways of thinking about lattice gauge theories at that time, and we had no clue that it would be of interest maybe after 25 years or so in the quantum computer community, where many people have gone back to some of the things that we had done at that time. And so this is basically an extension of that. And so more recently, Harsh Singh, actually he was also a student at IIT Madras, and he just came and became my student at Duke, and he's now a postdoc at Seattle, University of Seattle. Han-Ching Lu is another student with whom I have worked quite a bit. In fact, I've learned quite a bit of math from him. He's a very brilliant student. And of course, Tanmoy and Rajan are old colleagues. They do lattice field theory, but they are now interested in doing formulating these field theories on the quantum computer. Of course, there are also other people with whom I'm interacting right now. So all of them contribute to my inspiration in doing this. So here is the outline of my talk. What I'm going to talk about sometimes might look very straightforward and simple. The idea is to get you started in a very broad way, and then towards the end I will maybe perhaps tell some results that might be of interest to experts. So if you are already familiar with what I am going to say, please hang in there. Maybe at the end you will learn something new. So I will review the basic ideas of the standard model, because that's important for me to explain why we have to change things when we think in terms of quantum computing. And then I will mention some of the computational challenges that Sayantan mentioned, which motivates my work, right? And that then will lead us to understand how the challenges have to be sort of readdressed when we think in terms of quantum computing. And then this is the more exciting new result, I would argue, where we actually show that even with these qubits, we can actually study some of the holy grails of high energy physics, which is buried in asymptotically free theories, and I will show you a simple result that comes out of that. And then I will summarize my talk. So let's go back and try to understand a bit about the standard model of particle physics, which is what we would like to at some point start studying on a quantum computer. So if you go back to the origin, one might say, where did particle physics all began? Maybe the Western philosophy is that maybe it all began with Democritus, where people were thinking about what is the origin with which of matter with which we deal with it every day. But of course, some of my Indian colleagues have pointed out to me that there may be a similar thing that was going on in India at that time. So the question, of course, is that if you think about what the debate at that time was, and this is going to be the theme of my talk, was whether matter, when we think about it, should be thought of as some kind of a continuum that can be divided infinitely, right? That can be divided infinitely, or maybe at some point we just end and it becomes discrete, and that's all. The whole universe is built out of those discrete degrees of freedom. There was a nice cartoon in Google that I found which sort of describes this interesting debate, imagining what might have happened between Democritus and Aristotle, right? So Democritus thinks that the way to think about matter is it's like sand, where at the end everything is like a discrete set of particles, whereas Aristotle thinks no, we should actually think about it as water, where the notion of a tiny particle that sort of defines water is not there, right? But then of course most of us are not as deep thinkers, so maybe we fall in one of these two categories. So some of us might feel, well, this is all speculation, right? Unless there are experiments to prove one way or the other, it doesn't matter. But then maybe there are also wise people who would say that maybe we just have to wait for another 1,000 years where we might have more evidence and one of this will come out to be true. And that's going to be the theme, and I will explain why this happens in some of the things that we are going to talk about. So the question we are going to ask is, maybe there is indeed ultimately a discrete thing, so Democritus wins, and they're all qubits. Okay, so that's sort of the punchline, if you wish. So what is the modern perspective of the atom, right? We all know this, that the atom, at least in some sense, is made out of some kind of a quantum wave function of the electron being attracted to the nucleus. But then if you look into the nucleus, the story doesn't end there. It's made out of particles, which are protons and neutrons, and today we think about these protons and neutrons as even more complicated objects. So you see, it continues to go and divide. You keep going further deeper in, and so it's made out of quarks, maybe some gluons, and maybe there are other excitations around. And so the theoretical framework today that we try to understand this is through this theory called quantum chromodynamics, QCD in short, which is an example of one of our favorite quantum field theories. And so if we want to understand nature at some point, we have to understand more about how we formulate particle physics through these quantum field theories. So what is a quantum field theory? We all learn in our studies that an important ingredient of this is quantum mechanics, right? But then we also have to combine it with the simpler form of relativity, not the general relativity, but just the special relativity. And so we need to marry these two sort of different concepts, right, into a single framework, and quantum field theory helps us do that. So if you think about this question, I would say it's a theory that describes point-like quantum particles moving and interacting with each other, but then there is some important symmetries of nature that we want to preserve, right, and those symmetries must be incorporated into the theory. Now the standard model is sort of a theory like this, right, which has many particles interacting with each other, and it has roughly around 20, maybe plus few more parameters now that we know neutrinos perhaps have masses and how to explain those masses. This is actually a new revolution in the last 2 decades, so we'll have to understand that better. But if you think about the particles in the standard model, we have something that we call matter, which is made out of quarks. There are 6 varieties of this at the moment, and maybe if we do more experiments, we might find more ways of thinking about it. There are 6 varieties of leptons, and then these interact with each other through what we call gauge degrees of freedom. We call them gauge bosons, and of course the latest discovery was the Higgs boson almost a decade ago now. And if I think about just the proton part of it, the nucleus part of the atom, that just involves, remember, the up and the down quark. All of these are also there in some sense, interacting with the gluon. There's the gluon, and that is what we call the QCD, and that's the most difficult part of this whole theory. So it's easy to write down this theory as a quantum field theory, but it's very hard to do calculations that involve the interactions of quarks and gluons. And that difficulty is what motivates some of us to think about new computational techniques to solve the standard model. Now, of course, one might argue that there are also other interesting physics that exist at high energies, which might be equally interesting, like the strong interacting sector. And so in general, if you want to study the standard model of particle physics, I would argue that there will be some computational bottlenecks as we go think about it. So let me talk a bit about the computational challenges that we face as we think about it. The first thing I want to talk about is this new interesting experiment that is exciting us to sort of thinking about new physics. But let's think about what is that physics, right? So we think about the anomalous magnetic moment. So the physics here is that if you have a spin half particle, and if you think about the fact that it is charged, it has a charge E. Any charged object, if it is spinning, it's a spin half. So at least classically, it will have a magnetic moment that will get generated. Here it's quantum mechanically interesting because it's like a point-like particle. Still, there is a magnetic moment that you can actually compute for such a particle. And there's a very simple formula one can write down for a magnetic moment of any fundamental spin half particle, right? These are, remember, E is the charge of the particle, ME is the mass of that particle. This GS is sort of the interesting dynamical thing. It's something that you need to calculate using the rules of quantum field theory, right? And when you calculate it, typically it is written as 2 times some quantity, which is written as 1 plus delta, where delta is usually the thing that comes because of interactions. So if it was a free Dirac particle, the answer would just be 2. And I'm sure many of you have learned that when you do the Dirac equation. But then the more difficult part is this delta, and delta is something that you need to really know the rules of quantum field theory to calculate. So people have calculated these for various spin half particles, and the most interesting ones are that for the electron, and this delta theoretically has been calculated, I think, to 4 or even 5 loops. This is perturbation theory, and you get it very, very accurately theoretically, and then experimentally also it has been computed, and you see the experiment and theory match excellently, right? And so this is one of the triumphs, I would say, of quantum field theory, quantum electrodynamics, right? Now if you do the same thing for the muon, again there is a theoretical calculation, and then there is an experimental calculation, and now if you start comparing these two, there is some discrepancy between the two, right? Within errors they don't seem to agree. In fact, this was actually a very recent result, and this is causing a lot of interesting debate and question about, have we seen something beyond the standard model, right? So remember, these calculations are done within the standard model, and this is an experimental result. If they don't still begin to agree with each other and there is real difference, then maybe some new physics is being observed. But the point I'm trying to make is not in that small difference, which is of course exciting all by itself, and that's the beauty of physics, right? In physics we want to understand even those small differences. What I'm going to talk about is the proton, right? Here experimentally we know it very accurately, and notice that theoretically we are just way off, right? We have absolutely no control of our calculation in this, so you can easily compare the difference, right? So what is it that makes this proton really different in the calculus? It is so difficult, and here is a result in 2015. Maybe there are other results recently, I have not looked at it carefully yet. So that's your experimental value, right? Very accurately known, and this is like sort of the result that I just gave you theoretically comes from what we call the lattice formulation of quantum chromodynamics. As we will go further, I will explain what that is, right? And it's clear that the error bars are very big, and in fact this axis is what we call the quark mass axis, which is written in terms of the pion mass. So when we do the calculation, there is a free parameter which we can tune to the physical value. To do the calculations at the physical value is usually very hard, but these days with very extensive classical computers, people are beginning to do these calculations, but you can easily see still the error bars will be huge compared to what the experimental error is. So this is almost an impossible task at the moment. Now that's not the only thing. For example, if you think about many quantities in nuclear physics, for example, here is a binding energy. We all know that if you take a proton and a neutron, there is a binding energy. They bind together to form what we call a deuteron, and we can actually compute the binding energy. Again, the binding energy is known very accurately in this case, right? That's the experimental number. And almost 10 years ago this calculation was done, and even now the calculation is not very different. The error bars are like huge. It's very hard to do this calculation. And also remember that the physical value of the pion mass is here, and some of the calculations are done at very large masses, right? And so these are the computational bottlenecks that we face using a classical computer. And so the question is, of course the motivation of some of us is there some hope in the future that we can get these things better controlled? So why are the calculations involving electrons and muons very accurate, but not for protons and deuterons, right? Things like that. So to understand what the difficulty is, you have to understand what is the difference between the theories, right? Why is electron and muon, remember all three are quantum field theories. In one case it's easy, the other case it's hard. What happens? So let me go back and remind you a bit about what quantum mechanics is, what special relativity is, how we combine these two to understand quantum field theory, and then explain to you how we start thinking about the problem. So we all learn quantum mechanics even at our undergraduate level. So we are taught, the first example that we are taught is we put a particle in a box and we ask what are the wave functions of this particle. We solve the energy eigenvalue problem, you know what the ground state is, and so on. So one of the things when we do this, we learn this very important fact that the position and momentum are no longer sort of classical numbers. They have some very interesting uncertainty principle built in, and so we learn that x and p actually are matrices. By the way, this relation will play an important role later on when we think about qubits. Remember that these matrices must be infinite dimensional before we can even make this kind of a relation. You can try building these matrices, two matrices. We know matrices don't commute, but if you try to build two matrices such that it gives you an identity on the other side is almost impossible unless you think in some infinite dimensions. So typically when we learn quantum mechanics, we learn that, well, properties of the particle like the position, the momentum, the angular momentum are all matrices, Hermitian matrices. Their eigenvalues represent what we measure, but the time is not an operator. It's just a parameter that labels how the state is evolving, right? That is a bit of a problem when we learn special relativity, right? In special relativity, we realize that actually you can be in two different frames, and what you call as time and space is different from what I call as time and space. So these two are just variables that transform in a particular way, right? And that's the transformation we learn. So now the interesting question is, in quantum mechanics, one was an operator as a matrix, the other was at label times. How can you sort of mix these two? It doesn't make sense, right? So this is one of the things that we push under the rug. We teach you both special relativity and quantum mechanics as two different courses, till you come to a more different class where we start learning a bit about quantum field theory. So in quantum field theory, we first have to erase your notions of what a position is. A position is no longer an operator, right? And then all your hair stands up, and then you have to see if it's not an operator, what have I been learning, right? We then tell that space and time are both actually equal. They are both sort of labels where particles can exist. Remember, quantum field theory was a theory of particles, right? Point-like particles. So x and t just tells you where the particle is, right? So there is a manifold, right, where there is a point, and then at that particular point is where the particle is, right, in some sense. But then where is quantum mechanics built in, right? So we think about quantum mechanics at every point in space-time. Remember, space-time was just a label. So at every point we build a quantum mechanical system, right? And that's why we have a quantum field. The field lives in every space-time point. And so then the question is, if you pick any point and then you ask what is the quantum state there, well, we have to think differently now, because position is no longer an operator, position is just a label. So we say whether the particle exists there or not, that's a state, right? So we say there is a Fock vacuum, that means it's a vacuum state with no particles, but it's a Hilbert space state in your quantum space, right? And then there may be one particle sitting there, that is another state, and then there may be two particles and maybe more particles, right? So these are the states of your quantum system on that space-time point, right? So of course a quantum state, remember we learned superposition, so now we can also superpose all of these states, and that will be the state space on that particular space-time point. The reason I want to emphasize this is exactly going to come back when we think and build quantum field theories using qubits. So at every space-time point, if there was a particle which was bosonic, right? So we know, we've learned in quantum mechanics that there are particles which are bosons, there are particles which are fermions. At each space-time point, we say that, well, maybe there is no particle there, Maybe there's one particle. If it's a boson, there can be many particles. In fact, infinite number of particles can exist on that single site. Now you might say, why do we need an infinite number of particles on that single site? But interestingly, that's the way we have constructed our quantum field. A bosonic field will be, the quantum field for a boson will be a field or an operator that lives on this infinite dimensional space. And this is going to come back to us and haunt us, right, when we do quantum field theories. So the local Hilbert space for a boson is actually infinite dimensional. What about fermions? Well, they are more kinder to us because you cannot put more than one fermion on top of each other because the Pauli principle, right? So there, maybe the fermion doesn't exist or it exists, that's all. There are only two states. And that's nice. Maybe there's already a qubit there. So we'll see that is the fermions which are nice for qubitization of our theories, but bosons, which we know for other reasons, are not so nice, right? Higgs, we know there is a Higgs boson, we know there are gauge bosons. So this will be the interesting question. Do we need this infinite dimensional space at every point to even describe this theory? Now an important point to take home is that the absence of any particle anywhere in the universe, right, from this theory is also a state in the quantum Hilbert space, right? And that's one of the things that we learn when we do quantum field theories. So, but then there's a problem, right? The space-time itself is continuous, right? We don't think that in a small region there's only few points. There are infinite set of points even in a small region. So does that mean there's a quantum? Remember I told you that every point has a quantum Hilbert space. So that means at every quantum Hilbert, every point, is there a quantum Hilbert space? Of course, from the quantum field theory perspective, that is true, that every point has a quantum Hilbert space. That's when there is a quantum field. But then this is what causes a lot of trouble when we teach courses in quantum field theory. And when you do calculations, we just get a lot of infinities, right? So this leads us to the other next question about continuous versus discrete debate, right? So in fact, I've heard anecdotal evidences, I'm sure people here know maybe better, that even Dirac towards the end of his days was really puzzled and confused about these infinities of quantum field theories, right? It was very hard to understand what was going on. So everybody who thought about quantum field theory in this continuous manifold was puzzled what is going on. I think we got the answer when we started thinking about this debate. Should we think about space-time as being continuous or perhaps it's discrete, right? And this is what Wilson proposed, and there he started bringing the idea of condensed matter physics. In condensed matter physics, we always know that sort of electrons live on sort of atoms and then they hop around. So we don't ever think about the space between the atoms, right? And all of interesting quantum mechanics comes from a crystal structure, right? So Wilson thought maybe that's the right way to think about even space-time. So he proposed that we should think about space-time as a lattice, right? We shouldn't think about it as a continuum. He said that the continuum physics that we all sort of learn and know how to do calculations actually come when the lattice spacing becomes very, very small compared to physics, physical length scales. And that's what he called the continuum limit, right? I might say, well, you have a lattice, how can it become small? It's like fixed. And this was something that used to confuse me quite a bit when I learned lattice field theory. It's always there, right? You can't get rid of it. But on the other hand, if you think deeply, what Wilson was telling us, that suppose there is a theory on a lattice. Suppose there is a parameter in your theory that you change, right? But you change it in such a way that the physics remains exactly the same. But what happens is that the lattice spacing somehow reduces, right? What does that mean? Here is a sort of a toy example of what might be happening, right? So here is your proton. Remember, we wanted to study a proton. So let's say you decide to study this on a space-time lattice. This is what people who do lattice QCD do, right? They take a proton and they put a lattice. Here's a space-time lattice, right? And so here is your proton. This is just a rough estimate of what's going on. So let's say we take the size of the proton, which is like a, let's say, a physical length, right? And that size, I call it as xc. So in this example, this xc is 4 lattice units, right? So what Wilson would say is that if you start with this, right? You have some parameter in your theory. Now you change that parameter in the theory. If you change it, what is going to happen is you're going to get that. The proton will remain exactly the same, nothing happens to the proton, but now notice C is now 8 lattice units, right, in its length. So the proton remains the same, is the lattice unit becomes smaller. If you think about the lattice as important as we do in condensed matter physics, the length scale has become larger, right? You can do that and change the parameter again, and you get another parameter for which the lattice spacing has now become much smaller. The proton remains the same size. It's just that now it's described by lattices which are much finer. Again, notice this C is now 24 lattice units, right? So what is happening is that the physical length is diverging in units of the lattice spacing. So if you keep the physical length fixed, then the lattice spacing is reducing to 0. So Wilson's point is that there could be a parameter that I tune such that this C will actually be infinite times A. And then maybe when I look at my experiments at the order of C, the lattice has now disappeared. I get a continuum theory, right? So that's the way he started thinking about the problem. So Wilson said QFTs emerge from lattice field theories when physical lengths diverge in lattice units. And that is a very deep step, because now he brings condensed matter and high energy physics in one footing, right? So he connects high energy physics, where we are thinking about no lattices, continuum physics, whereas in condensed matter physics we think about a very nice system of lattice. There's no infinities, there's no problem, right? And now he's saying that the two are actually connected, where if you start with the condensed matter system, maybe there is a parameter, a tuning parameter that you tune, and there are two phases in the theory, let's say, and there is a quantum critical point at 0 temperature where the correlation lengths diverge, and close to that quantum critical point, if you want to understand the physics of any massive theory, that's where the physics becomes universal and interesting, and that's where the quantum field theory arises, right? So QFTs arise near second order quantum critical points. So every second order quantum critical point in condensed matter physics, one can think and try to understand what is the quantum field theory that is emerging near that. Can we write it down and figure out? He went one more step further. He explained to us exactly what is the right way to think about it. Yes? Can you say that again? Oh, yeah, it's just that I was thinking about a condensed matter material where you can think about this as a parameter in your Hamiltonian, and then you can always heat up the system and think about it as a temperature. And typically when we think about quantum critical points, you define it at 0 temperature. That's why it was just an axis to explain that. Thank you. So what Wilson then explained to us was that if you think about all lattice theories, right, at a microscopic level, a theory of all microscopic models, what he sort of explained to us was that the quantum field theory is a very fine-tuned point in the space of lattice models. It's very hard to figure out where that point is, right? It's very fine-tuned. You have to figure out where exactly all the terms in your lattice model have to be obtained from, right? On the other hand, what one can do is we can start with any lattice model. As we tune some parameter, what happens is there are few parameters which are important, which we call renormalizable parameters in quantum field theory language, which are basically relevant operators, and then there are certain things that are non-renormalizable or irrelevant operators. And so if you can tune your system such that all the relevant operators are 0 and you're on what is called a critical surface, then at this point the long distance physics will be described by the quantum field theory, and this is exactly what happens at quantum critical points, right? So you have to start with any lattice model, you tune your parameters, and then if you come up with a second order critical point, the long distance physics will be described by some kind of a QFT, right? What is a QFT? That will be an interesting question which we have to understand better, but that's the way we understand QFTs non-perturbatively. Until Wilson told us that, most of the calculations are all perturbative. That is why we could start now doing calculations in lattice QCD, which is a very non-perturbative theory, right? So you could start with either this model or that model, it doesn't matter. Both of them at the quantum critical point will give you the same physics of the quantum field theory, and this is where universality begins to come in, right? So different theories can give you the same physics at long distances. So if we have this background of Wilson and try to understand quantum field theory, then we can say, what about quantum mechanics? Should I have been taught quantum mechanics in a different way, where positions were operators and momentum were operator but time was not? There's a very nice description of quantum mechanics in this QFT language, right? And this is something that's often useful to understand the connection. So suppose we go back to the quantum mechanics of a particle in a box, right? What Wilson would say is, don't think about this particle in this continuum, discretized space, for example. We don't have to think about even space-time, because I'm thinking in the Hamiltonian approach, right? So then there are all these particles, all these other places where the particle doesn't exist, right? So these are all Fock vacuum states, right? The particle is existing there, so that's where you put the particle. So there is a state here which is the Fock vacuum state, here, everywhere. Here the state is the particle existing there, right? So that's the way to think about this thing. So notice now suddenly the particle's position is no longer an operator. All that is an operator is whether the particle exists in a particular space point or not, right? And then of course maybe there is a parameter that I can tune such that all these space-time points come together and you get back your continuum. So in this viewpoint, if you think about quantum mechanics, then notice there's something more interesting that can happen. We thought that this was the physics of a single particle, but then quantum field theory will say, well, what about if there was a particle on the other side, and maybe there is a particle antiparticle, so that this is also in the same quantum number sector as this particle, right? So here there is a particle, but then there is a particle antiparticle, so the particle number, quantum number is the same between this and this, and so I can add those two because superposition tells you that that's also a part of the game. And then maybe there is another particle antiparticle that have been created somewhere else, right? And then so on, right? And so clearly a quantum field theory approach to quantum mechanics will tell you that there are many more states rather than the single particle state that we may have to take into account. Now your Hamiltonian might tell you that, well, these are all 0, we can only do this. Then you are doing quantum mechanics. But if you say your Hamiltonian allows all these particle creation annihilation events, then this state can go to that state, can go to that state, right? It can then become a superposition of all of those states. And so the ground state will be some superposition of all of these states. So even a single particle in quantum field theory is actually a superposition of an infinite number of entangled states. So quantum field theories are difficult to begin with, right? Because there is quantum mechanics at every point in space-time. So why are the calculations involving electrons and muons very accurate compared to protons and deuterons? Well, now we know what the answer is. Electron and muon have some kind of Hamiltonian such that the quantum states are dominated by only a few states where I can do perturbation theory and understand what the answer is. So on a piece of paper, of course, you need to be a graduate student and do a PhD for almost 5 years before you can even do that calculation, but it's doable, right? On the other hand, even if you spend your entire lifetime doing this calculation for a proton, it will be almost impossible because it's a superposition of many exponentially large number of entangled states, and you don't know which is important, which is not, right? If somebody can figure out which are the important states, there you go, you get $1 million for that. No, just from the fact that particle can get created and destroyed, and it's a strongly coupled system. Yeah, so you're right that you can think about it in the continuum, but in the continuum sometimes to figure out the measure of how to add and subtract things become much more subtle, right? So remember, you have to create, let me go to the next slide and then maybe I can explain to you. So suppose you take a proton, right? You have 3 quarks.
Scale which is required. That is what is required in the entangled state also.
Right.
Whereas the electron muon, the scale at which you can describe an isolated particle can be much smaller.
Right. So, but do you disagree with some of the things that I said?
No, they are not. But what is the entanglement may be an issue of locality versus non-locality. That's what.
Sure. There may be scales involved that is also important in this discussion. I completely agree with that. So if you think about a proton, you cannot just think about the 3 quarks. So there was something called a quark model that people invented and maybe just thought about it as a quantum mechanics of 3 quarks, but unfortunately that doesn't capture the whole physics because you have excitations of gluons. I just put it as dots there, but then there is people in fact today talk about, although there is no S quark in this, but there is an S quark condensate that you can actually compute inside a proton, right? So there's a lot of interesting complicated dynamics that come through. And now your question was, why can't I do this whole thing in the continuum, right? In the continuum, when you try to do this whole thing, there's a question of even the measure of what you're going to do when you're trying to create a particle here and there, right? It's like, if you think about it, if you do a path integral, for example, right, even in quantum mechanics, the path integral becomes very jittery, right? And so you have to develop a lot of mathematical skills to do that. And sometimes it's even difficult to do these things at a quantum field theory level. So you can do perturbation theory, which is what people do, and they actually sometimes build a class of diagrams which gives you some quantity which is helpful. But then if you really want to get the proton, so far as I know, nobody has known how to do this in the continuum to get all the measure factors and all completely correct. Exactly. That's another way of thinking about it. So there are exponentially large number of terms if you really think about it in terms of just doing perturbation theory that are important here. So of course it's not very surprising that in quantum chromodynamics it's hard to compute quantities. So it's like climbing a hill with a lot of rocks, and so the question is, and also remember that you want to, even if you do it in the lattice language, you want to go to the continuum limit to get the physics, right? So the number of degrees of freedom that you want to think about becomes much more involved, right? So it's all a pretty hard thing. So the question is, somehow can we think about, if you take this lattice more seriously, perhaps our universe is some kind of a correlated condensed matter system, right? Can we then maybe try to build a condensed matter system to sort of model our universe, right? And that is the stage in which people are trying to think now. because typically a quantum computer, as we'll see in a minute, it's very natural to think about quantum states and evolving them in time. So if you want to create a quantum state of a quantum field theory, maybe evolve it using a quantum computer in time, and then do some measurements and see if some of these calculations are easily done. So let's try to think a bit about what we are trying to do. Suppose you don't have a quantum computer. Why is it hard? As I just already mentioned to you, from a classical computation point of view, suppose you want to calculate the proton wave function, right? What it is. Well, it's a vector in some infinite dimensional space, as we already talked about, right? But let's say we make it finite dimensional somehow, right? But then still, if there are many directions in this vector and we just want to find one vector, when we think classically, we think in terms of components of a vector using some convenient set of coordinates, right, which are usually local coordinates, right? We think about some local Hilbert space, and then we say, how is my vector coming out in terms of this local Hilbert space? So we need to find an exponentially large number of coordinates, right, because it's an a large dimensional Hilbert space. So all of those numbers we need. Then we'll know what the proton state is. It's just calculating a vector. That's like searching for a needle in a haystack, right? You have to find all these numbers exactly before we know what a proton is, right? Now, of course, if you had an approximation and if you understood the physics of some length scales and figure out, okay, these are the most important degrees of freedom, then maybe we can say, well, we don't need all the different coordinates. All we need is maybe 10 coordinates to understand the proton. That would be a big breakthrough. That would be interesting. Right. For the proton, as far as I know, this has not been doable. So classical computation is exactly like searching for this vector in a huge dimensional Hilbert space. Now, people have done this. In fact, statistical mechanics is very similar to this, right? Because we know that the statistical ensemble of possible states is exponentially large, but then the physically interesting states are very small, right? And people can actually figure this out and use methods like Monte Carlo methods. And this is exactly what we do in Lattice QCD usually when it works, right? So there what you do is you take your state and then evolve it in imaginary time, and then we ask whether that imaginary time evolution can be written in terms of some path integral, right? Where all the measures, everything can be done carefully. And then we say, well, maybe a computer can sample the space and figure out the most important contributions. But in real time, all this just breaks down, because in real time, you have to evolve the state using a unitary evolution, and now you have all complex numbers into the game, and so there is no sampling probability distribution anymore, right? In fact, these unitary matrices are exponentially large again in the vector space. So real-time calculations are really hard for large systems. So these challenges, in fact, even doing the imaginary time evolution is not always doable in things like there are times when you get into a sign problem, something like a problem like this, right? And these are all referred to as sign problems. So this is one of the challenges that actually motivates me to think about this. Is there another way to think about this whole system? So can quantum computers help in this case? So the steps here is that a quantum computer, instead of storing bits, actually stores a vector, a two-dimensional vector. So already the space is like a two-dimensional space. Now if you have many qubits, you have a product space of many two vectors, right? So suddenly you have a large vector space, right? Exponentially large vector space. And quantum computers can evolve these vectors when the quantum computers are available with any unitary time evolution you like, right? You just have to design the gates appropriately. So for example, if you start with some unentangled system of qubits, you can go through a circuit which is made out of these quantum gates, each of which will implement a unitary time evolution, and then you can put all of them together to get a new state which is typically an entangled state of all the three, right? And now you can think about doing this whole thing with 100 qubits when these things are available, and suddenly you're able to figure out the time evolution of a 2 to the 100 by 2 to the 100 2 to the 100 dimensional vector space, and the whole time evolution is just being done through these gates. So a quantum computer takes care of all of those calculations for us. Now I'm not telling it will be available tomorrow or maybe in 5 years, but at some point if this is available, this would be like a breakthrough, right? It will be something we could think about. And today a lot of work is going on in terms of what type of algorithms you can build, how to do the measurement, what is the scope of this whole thing, and this is a new field of research. Yeah, but unfortunately, as far as I understand, there's also a noise because all these qubits are not completely coherent and things like that, and then the number of gates are also sort of limited. You cannot do whatever you want, right? So there are some limitations, but you're right. So sometimes, in fact, there is a paper by Google which says that it can do something that cannot be done on a classical computer, but it seems like a more academic problem than what maybe we would like to have. Yes. Fair enough. Yeah. So good point. I'm just trying to give the most simplest description of what can be done. Yeah. Yes. Yes.
So while doing the measurement, it may significantly destroy the advantage during this computation. So
that's a good point. If you don't think deeply enough, that is what it seems. But people have designed that measurement process also as a process with gates. So what it does is, typically any measurement process, remember at the end is some kind of a mod square of some matrix element. So you can think about that as coming from some unentangled gate to a state, and from that state to an unentangled state. So you can actually think about this whole measurement process in this whole way, but that's an algorithmic issue. But you're completely right. So these are things that you will have to think about, make sure that it's all doable, and people are already doing this in some cases at least.
Okay, sir. Just one more question.
Sure.
Just go to the previous slide where you had the box, means particle in a box.
Oh, particle in a box. Can we come back to that later on during the question and answer session?
Sure.
Yeah.
Has it been at least theoretically proven that quantum computers will actually give advantage over classical computers in these calculations? Theoretically, at least.
Yeah. So in theoretically, without any issues of noise and all, it's almost obvious that once you are able to have 100 qubits, for example, if they're all, I'm able to do a 2 to the 100 times 2 to the 100 time evolution of the system, right? It's sort of obvious that I cannot do on a classical computer.
No, but the actual calculation which one does in these theories, will it actually give an advantage there? Has it been shown theoretical advantage of?
The reason it has been, I think I would say theoretically shown, but maybe not practically, because there are no such calculations.
Okay, thank you.
Yeah. Okay, so what we would like to do is not get into quantum computing, because I'm not an expert in it, but there are many interesting questions here. What I am trying to ask myself is, even before I put the system on a quantum computer, what is the state space I need to start with, right? I don't know what that is, right? Remember that at every space-time point, I have to think about what is the Hilbert space at that point, right? And I already told you that the dimensionality of the state space at every point actually, right, depends on the type of particle. For fermions, it's okay, it looks like a qubit. There are some complications because the fermions obey the Pauli principle, so I will not get into the details of that. That's an interesting question, but it at least looks like a qubit to begin with. But then a boson is an entirely different question. A boson, the local dimensional Hilbert space seems infinite dimensional. So can I even do anything with a bosonic field theory on a quantum computer? because I have to really change the way I think about this, right? And that is what will take me to the theme, the sort of the final theme of this debate between continuum and discrete, right? So here the question is, can I take a continuous field? Remember, it was a continuous phi. Phi was a real variable, if you wish. Often it's like a infinite dimensional Hilbert space at every space-time point. And so if I think in terms of sort of particles, I should have all the way from 0 to infinite number of particles before I can describe this continuous field. And now I want to change that to a discrete qubit field, right? Maybe I want 3 qubits, ideally only 2 qubits, right? Or maybe 1 qubit, that will be great, right? Can I reduce the number of qubits at every point before I can start thinking about my field theory, right? And that is what we define as qubit regularization. Remember, regularization has been used as a word in quantum field theory. You have a question? Regularization has been used to remove infinities, right? So regulate the infinities. We are using the same kind of word here, and we are arguing that maybe there is a new type of regularization that we need to do before we can put bosonic field theories, which involves scalar particles and gauge particles. Gauge particles are also bosons, right? So from the perspective of RG, all we are saying is we want to design lattice models with a finite local Hilbert space, right, on each site. In fact, in terms of gauge theories, it will be on a link, right, which will be in the same basin of attraction as the desired QFT. So for example, if this was your traditional model with an infinite Hilbert space at each site, this would be another model with just maybe few qubits per Hilbert space, per lattice site, right? And so there will be a quantum critical point even in this that will flow to the same quantum field theory, and that is sort of the goal of our question, right? This is something, as I told you, we started thinking about it long ago, but only recently we have begun to understand it better, I would say. There are lots of interesting questions that we would like to explore with this. So of course the final question is, what is the minimal number of qubits I need per lattice site where I can really reproduce my original QFT? So one of the holy grails of quantum field theory is asymptotic freedom, right? Non-abelian gauge theories have this interesting feature. So the question is, can we get asymptotic freedom using this idea? So a quick introduction to asymptotic freedom. These are the physicists who first proposed that this was an important principle to understand the physics of the strong interaction, and the main sort of thing about this asymptotically free theories is that often the quantum field theory has no free parameters. This is, I'm talking about the ideal scenario, right? So it's a very beautiful quantum field theory with no free parameters, and the parameter that you think exists, there's always a coupling, actually just sets the scale of the problem, right? And this is something that people have measured, what we call the alpha, the strong coupling constant, and in QCD there's a prediction of how this should obey. We can predict it in perturbation theory very nicely, but as you go farther and farther away, it becomes non-perturbative, and there are calculations now on the lattice which also give you some interesting results. In fact, this is the lattice calculation, and this I think is some other calculation that comes from tau decays. So they have a very rich physics, right? It's a theory with no scales in the problem, but still scales arise dynamically from this theory. So in 4 space-time dimensions, of course, non-abelian gauge theories are known to be asymptotically free, but of course, as you can imagine, when we want to study these things on a quantum computer, or at least begin to understand them, we're going to begin at a much simpler level. But can we construct an asymptotically free theory with just 2 qubits even in a simple model, right? But there is a challenge, and I'd like to point this out. If you do this on a lattice, right, there's of course a lattice scale. This is something that's well known. Wilson told us this, right? You have to tune yourself to this critical point, and only at long distances will we get the physics right. But in an asymptotically free theory, there are scales which are physical all the way from the ultraviolet to the infrared. It is not just the infrared. There is also the notion of ultraviolet. But what is ultraviolet on a lattice theory? Right? It's a bit confusing. So in fact, the way to think about asymptotic freedom in a lattice theory is to think about three scales. Right? One is the lattice scale, where you write down your model using qubits. Right? But then there will be a scale where the ultraviolet physics of the continuum emerges. Right? This itself will be several lattice units from this. In fact, ideally this will be infinitely far away from that. But then there is also another lattice scale where all the masses and the correlation lengths emerge. So the physics is universal in this whole regime of length scales. What is non-universal is of course the lattice, because remember, different lattice theories might have different physics here, but they will all give you the same physics in this farther region. And so it will be hard to do this directly in 4 dimensions, because they'll have to study this whole different regions of scales, right? So the ideal thing is to consider some simple examples. So the example that I'm going to think about is one of the simplest examples we all learn to understand asymptotic freedom, is the O3 nonlinear sigma model in 2 dimensions. There is one space and one time, right? So what happens is, this is a theory. I'm going to directly go on to the lattice description instead of thinking about the continuum. So there is a quantum field at every lattice site, which is a unit vector, right? And then that means there is a particle. Remember, there is always a Hilbert space on every lattice site. The Hilbert space now is a particle on the surface of a sphere, a unit sphere, right? The conjugate variable here, momentum, is just the angular momentum. And so we can think about a particle at every lattice site moving on the surface of a sphere, and all these different particles now interact on different sites. Okay? In the continuum, of course, if you write down, you will have a simple action. This is the coupling that I mentioned about. You can argue that there is no dimensionful parameter in this case. So this is the coupling that actually gives dimensions to the theory. So it has been studied extensively, right? And in the traditional lattice formulation, there is a quantum degree of freedom at every point, and that obeys the usual commutation relations of a particle on the surface of a sphere. So there is a position of the particle, the angular momentum of the particle, and the fact that the position is a vector, right? And these are sort of the symmetries that we will keep as an important description. So the local Hilbert space is actually infinite dimensional, right? You want to think about a particle everywhere on the surface of a sphere. So you can think about it in position space as particles on the surface of a sphere, or in angular momentum space, right? And if you want to keep the symmetries, remember, I want to think about the Hilbert space to be finite dimensional. So I have to somehow make this infinite dimensional into a finite dimensional space, and that will be the qubit regularization that I will do, right? There is a well-known lattice Hamiltonian of the system, right? And then there is a continuum limit, right? People have studied this continuum limit, and the way they do this is they would put the whole system in a box, right? Remember, there is no scale in the problem, so you put the system in a box, and then in that box you measure some length scale, a physical length scale. Now, if it was a scale invariant system, if you plot this quantity, which is the length scale at 2 times the box size divided by the box size, right? And if it's scale invariant, then C of L will be proportional to L, so this will just be a 2, and it will be some value of CL by L. So a scale invariant theory will just lie there. However, if you had some mass scale in the problem, then there will be an interesting line here, and for this O3 model, this line was computed analytically and even on the lattice long ago. See, it was 1995. So the traditional model can really produce this line completely. The goal for us is, can we reproduce this using a qubit regularized theory? So if you do the qubit regularization, remember the goal is to take this infinite dimensional space and truncate it, find a finite dimensional space. And what we do is just take L equals 0 and L equals 1, just the two lowest angular momentum states, right? This is a 3-dimensional space, right, because it's spin 1. This is spin 0, it's 1-dimensional. So the total Hilbert space on every lattice side is just 4. Remember, the original problem had an infinite dimensional space. Now we're just going to do it with 4. So that's 2 qubits per lattice site. So the question is now, can I design a lattice model with 2 qubits per lattice site in 1 dimension such that I reproduce that solid line, right? And these models have been studied extensively in condensed matter literature. They are basically, they fall under the name of spin half ladders, right? There are 2 spin halves, right, at every site, and they are coupled in different ways, right? So you can do a lot of interesting Hamiltonians there. So spin ladder Hamiltonians, if you take the simplest one, looks like this. So there is a spin half chain here, there is another spin half chain here. They are coupled with some coupling here. They are all anti-ferromagnetic. The reason I take it to be anti-ferromagnetic is something I can explain later on if somebody asks a question. And then this is like a coupling in between. So if you take these anti-ferromagnetic chains and make Jp not equal to 0, then suddenly the whole chain gets a mass gap. And in the limit as Jp goes to 0, there are 2 decoupled spin half chains. So there is a critical point that the correlation lengths diverge. So some condensed matter colleagues actually suggested just take this and you will get your solid curve. So that was an interesting thing for us. So we took this problem and we studied 2 different limits, J1 and J2 being the same and J1 and J2 to be different, and then we studied what happens with Jp, and then here is what we got. Right? So we do see that the theory is massive, it's not scale invariant, but it doesn't really follow the solid line. So this was like a failure, right? So it does not work. So in fact I wrote to my colleague who suggested this, and then it was not clear what other models we'll get. So we explored a bit, and then finally we got the right model in this class, and that is what we call the Heisenberg Cone. Right? So again, remember there are only 2 qubits, but here this coupling is set to 0, this coupling is set to J, and this coupling is set to 1. And then in the limit, as I told you, remember this coupling must be small, but we look at it in a slightly different way. We say this coupling is large compared to this, and you get a critical point there, right? And then these are the step scaling function of that. So notice that I have results for 3 different couplings. J equals 3 starts off, remember for small lattices you will not see the universal physics, so it's off the black axis, black line, but then as you go to bigger and bigger lattices it starts following the right thing. If you go to slightly larger J, again you start off in the wrong place and then it starts falling. But interestingly, notice that the point where it starts meeting the black line has now moved up, right? And now if you make J larger, again it starts off wrong, but then it starts falling on this axis at this point. So what we would like to claim is that this 2 qubit model actually reproduces the physics of this black line in the appropriate limit, right?
What do you call Heisenberg Cone? You call it Heisenberg
Condo, I see.
Heisenberg chain.
With, yeah. Some people have called it the Heisenberg necklace. So this works beautifully, right? Now, can we do this for gauge theory?
I have a
Yes.
question. So when you did qubit regularization and you said this leads to an RG flow, I assumed that would result from changing the number of degrees of freedom you are looking at. So you reduce the number of degrees of freedom from infinite to say 4 on a single lattice point, and then you'll get RG by say increasing or decreasing from 4.
No, we are just going to bigger lattices.
Okay.
So that's the whole beauty of it. So you can actually write down a lattice model with just 4-dimensional Hilbert space at every site. There's 2 qubits, and we actually get the physics of the infinite dimensional thing. So both of them are in the same universality class.
Okay. Okay.
So will this all work for gauge theories? Well, we are beginning to explore this question, but there are reasons to be positive. As I told you long ago, we were thinking about this, and there is a prescription we laid down at that particular point. But there we were thinking about allowing ourselves to go to larger and larger Hilbert spaces at a single site. There we know that at the end, maybe for some reason you will get it back. But now we are asking, can we really remain in a smaller dimensional Hilbert space and still get the physics by just finding the right Hamiltonian? We have to search for the Hamiltonian, but then maybe there is a right quantum critical point where this emerges, right? So, so we are starting to think about how we can start with the traditional lattice gauge theory and do this kind of mapping. And I think what we are doing is not very different from some of the other work that has been going on even for many years. So we'll see where all this heads. So that brings me to the summary of what I wanted to say here. So if we can study quantum field theories, right, using quantum computers, as I hope it will happen at some time, we can maybe overcome many of the computational hurdles that we have today. However, to do that, especially with bosonic fields, there is a bottleneck that one has to overcome, and basically it is about the local infinite dimensional Hilbert space. So there's some reformulation that will be necessary, right? We cannot expect that each site will contain an infinite dimensional Hilbert space. Once we do that, have we lost some interesting physics? That's the question. Now, if we do that, we have reformulated the theory, and so we call that as qubit regularization. And the question we are trying to explore is whether all QFTs, not maybe just the O3 model, but all QFTs that we are interested in can be reproduced in this particular way. And we're just beginning, I think, to scratch the surface of this interesting field of research. Of course, at the end, the goal is whether our universe can actually be built out of qubits, and if all quantum field theories, the standard model, can be described using qubits, maybe we've made one step closer to understanding that. Let me stop there.
Thanks, Shailesh, for this wonderful talk. So, questions?
Sure.
You have completely ignored gravity.
Yeah, I've completely ignored gravity. You're completely right.
What is the point in talking about universe without gravity?
That's true. I completely agree. One step at a time.
Well,
So it's like, are we the seagull or are we the crab? That's the question.
well, actually what you are trying to describe is, can I describe my space-time, okay, as coming out of some kind of operators, the representations of some algebra,
Right.
which is in this case turns out to be probably simply qubit, or what you may call as the Pauli matrix algebra at every point.
Right.
That is the way so in some sense gels with many of the modern things which people from, say, let us say string theory or others trying to look at or even people who look at non-commutative geometry, etc., where they introduce non-commutativity at every point. Okay, that is the kind of thing which you are trying to do.
Yeah, sure.
So it seems to be that kind of framework in which field theories have to be built on such spaces rather than regular Minkowski space-time. That seems to be the picture which you are trying to explore. Let me put it that way. In that sense, there is a inbuilt regularization at every point,
Yes.
which is already there,
Right.
given by the scale of this thing.
Right.
Is my understanding is okay with you?
So remember that first of all, I don't even want to think about gravity. The only reason is because I want to think about a lattice description first, before I can even think about gravity, right? So since I'm not an expert in GR and how to think about triangulations and all that, people do this. So once you have a lattice description of the theory, then a natural question is what we have learned so far in terms of how to latticeize quantum field theories. A natural question is the infinite dimensional Hilbert space on each site an important ingredient to build our theories, or will RG naturally bring it out for you? And my question is, I think, much more, although I framed it as building a universe out of qubits, but my question is much more, I think, straightforward in the sense that can I get asymptotic freedom using just a finite dimensional Hilbert space at each site? The reason why I'm not sure yet, although I showed you some example where it works, is usually the way we do calculations when we show asymptotic freedom is we do Gaussian integrals. Right? Those are the free theories, and so we can do a lot of calculations using that. But once I qubitize it, the Gaussian fixed point is sort of disappeared from my analysis. So is it even dynamically possible to regenerate that or not is not even clear to me. So even this O3 model, right? Many of us, even including me, were almost certain we will not be able to do this using a few qubits. The fact that we could even do that seemed very surprising to us. So I would still say that we are maybe learning something, that maybe sometimes certain things in the continuum that we think we know or we can do calculations with can actually build out of qubits. And so in that sense I agree with you that we're just exploring if space-time, the way we think about it, can be constructed with local finite dimensional Hilbert spaces. Now if you say that this is obvious that it can be done, so maybe you know the answer. For example, because for example we know this for O3. If you ask me how do you do O4, I would not know the answer today. The hope is maybe I will know the answer next year perhaps, right? So that's the kind of thing. Can you do CPN models like this? Yes, that we have begun to understand that is more tractable. Can we do an SU2 gauge theory, the asymptotic freedom of SU2 gauge theory? I don't know whether we can do that or not. So if there was a no-go theorem that somebody could tell us that this is not possible, that would be an interesting step for us, right? So then if there is no such no-go theorem, I'm going to say if, then it becomes interesting that maybe we can think about at least quantum field theories in this language. Then the next question would be, how do we think about gravity? And so that brings up a whole big can of worms, and I don't even know where to begin for that. So maybe I know that there are theories where space-time itself is emergent from quantum degrees of freedom. I don't know how to think about it in that language. And I think Bhaskaran was mentioning that at some point you get things on a boundary which is quantum mechanical and all that. So this is...
Well, in principle what you do is emergent space-time, where finally you have qubits.
Yes.
And what you will get is in the continuum limit.
Right.
The conventional field theory or particles in Minkowski space-time.
Right.
Minkowski space-time has come out of the qubit algebra which you have built.
Right.
But in principle it is, the real space-time is more than Minkowski. So
right.
That's what gravity will tell. It's
right.
almost Minkowskian, if
right.
you want, flat almost.
Right.
So that's what is the goal seems to be. Yeah. And that works out very well to some extent. But my only concern is when you talk about these things, there is the issue of mass, which is coming from the symmetries at the local point itself, which is the Lorentz algebra. The Poincare algebra which you are trying to build, which will give me the mass. You don't have any of these things. So you bring in a scalar field, but you don't have a mass for that. Do you have a mass for that?
So notice in this model, everything is made out of qubits at a lattice point, and the whole mass is an emergent quantity because I'm able to reproduce the asymptotic free curve, right? So that has all the physics of the mass built in. So in a way, asymptotic freedom and masses and mass gaps all emerge from RG, Wilson's RG at long distances. And that's sort of beyond my calculational ability. That's why I use a computer to show this. But we seem to be getting all of that by not putting a mass term in our Hamiltonian itself, right? The Hamiltonian, remember, is just antiferromagnetism here, that's it. What should we call the mass term? I don't even know. It's just a condensed matter system. But the mass term is emerging out of RG in some very interesting and intricate way. So so the theory, I would claim, is massive, exactly like how you would have expected the O3 model to behave.
Okay. Sir, at first, thank you for the nice talk.
Sure.
Okay, sir, can you just go to the slide?
So which slide do you want?
The particle in a box. Where
particle in a box.
Yeah,
okay.
you just made, this lattice spacing.
Let's see. Maybe here. Was this the one?
I cannot see anything in the.
Oh, sorry. I need to do that maybe. Let's see if that works. Yep, there we go.
Yeah. Sir, as you said that according to, so first of all, this question of mine will be over simplified, but I think it's a really relevant question. As you said that if you, if we understand quantum field theory, then the vacuum state is also a quantum state, and a single particle state will be the superposition of all sort of states where particle and antiparticle is sitting around. Okay, so
maybe you're looking for this slide, maybe.
Yes. Yeah. So, sir, suppose this particle moves from the middle point to the corner of the box.
Yes.
That's, for me as a quantum physicist, that's a quantum state evolution.
Yes.
And it is well known that there is a lower bound in time taken by a quantum state to evolve. That's known as quantum speed limit. And it's a theoretical limit and fundamental. If quantum mechanics is true, this limit cannot be violated. Therefore, am I thinking this correctly, that this lattice spacing and the maximum speed limit, that's the velocity of light, and the quantum speed limit are interconnected?
Yes. That will emerge at the quantum critical point. So, for example, in quantum mechanics, we don't really worry about it because here I'm talking about non-relativistic quantum mechanics in that sense. I am just writing down a theory where, if you wish, on a Hamiltonian, right, on a lattice, right, I can think about a particle, if you wish. I have some quantum numbers, and then I have particle-antiparticle, which also has the same quantum number as a vacuum, right? So I can build out a lattice Hamiltonian which has this symmetry. Maybe if you have a pen and a paper, I can explain to you how that happens, right? So basically what I'm saying is, there's a particle, there's an antiparticle. The quantum number that's conserved is only the particle quantum number, right? So particle, antiparticle will have zero charge essentially, right? So then if I write down a Hamiltonian, of course all of these will be part of the game. But your question is, how does relativity emerge? What exactly is the speed of light? And these typically come about. Of course, you can start with the Hamiltonian, for example, the Dirac theory, and then if you write in the free Dirac theory, you can put it on a lattice, and then you can show that the speed of light comes out as it is, right? Because all you want to do is to take the lattice spacing to zero. That's a parameter in your theory. But in an interacting theory, usually it will come out at a quantum critical point, and that quantum critical point better be relativistic. So there are some quantum critical points which are not relativistic. So unfortunately, then you're reaching a wrong critical point. So you have to be at the right critical point, and then close to that critical point, the physics will be described by a particle with a dispersion relation, and then since this is all in the Hamiltonian approach, all that will set is what is the time and the space. There is some, remember, time and space always have some units, right, at the end of the day, and so you just have to figure that out, and then you will get the speed of light.
Okay, so sir, I am beginner, but this is the reason I am one of the believers of these discrete models.
Sure, yeah.
Okay.
No, it's
Thank you very much.
Sure. Yeah.
Hello.
Yeah.
So thanks. I mean, like, since it has been said, still I'd like to thank you again for a very nice talk.
Thank you for.
So my question is like, so how finally the time is taken care of? It's how it's like the number of gates we are applying in the system.
Yes. So typically in quantum systems, again, I'm not an expert in this, but the way I understand it is that each quantum gate evolves the system based on e to the minus I some time scale times h.
Exactly.
Right?
Right.
And so that will be the unitary operator.
Right.
And so if you want a particular unitary operator, what you'll have to do is put e to the minus I some epsilon, which is a small time h, and then you'll have to tune that epsilon to 0,
right,
and things like that. Yeah.
So can we conclude that physical time is just algorithmic complexity?
Yes, I think that's true.
Okay, I see.
So it's just a question of how many gates you have, and yeah, the complexity of what kind of Hamiltonian that is.
That's very interesting. But anyway, so I had another question, which like you had this, regularized qubit model. So you have Heisenberg Cone, right? Heisenberg Cone model is is the one which is actually reproducing a theory.
Yes.
So do you have any physical intuition why this kind of model actually can actually simulate the system in a much better way, like this kind of interaction are specific?
Let me understand that question. So what you're saying is how I understand that this model reproduces the physics of the O3 model?
No, so I'm asking, like, you had one model,
yes,
which is not exactly Heisenberg Cone, but that did not reproduce your expectation, right?
Yes, this one.
So, but then you change little bit stuffs in your model,
yes,
and then you actually got to reproduce the exact theory what you were looking for.
Right.
So is there any physical reason behind that? I mean, like, why
yeah, so this is a very interesting question, and just I was visiting ICTS, and there is a professor there, Subro Bhattacharya.
Okay.
And we had a conversation about it because my intuition of condensed matter physics is much lower than his. So he actually pointed out some very interesting reason why this might actually be happening.
Okay.
So apparently there is a way of, maybe again I should. So there is a way of thinking about this physical system. Remember that on each side there are two spin halves. So there is a spin 0 and a spin triplet. Exactly. Right? So there are both these states. Exactly. The question is, how do you take these two different sort of O3 quantum numbers, and then combine them in this particular way and figure out what is going on, right? Exactly. So naively we thought that, well, J is 1, so typical, and it's antiferromagnetic, so spin zeros will be the most important degree of freedom, at least on each side. But then on the other hand, this J is also becoming very large. So what he would argue, and this is something we are thinking about, it's not completely determined, that one has to really integrate this chain out. And as we integrate this chain out and see what kind of, because these are the large J's, right, so this then induces some interesting dynamics between the yellow spins. And if you think about how the Berry phase terms and all that cancel, you might be able to see the O3 model emerge. And he showed, at least there are some calculations he did on the blackboard which suggests that there is something called a theta term that arises in this spin chain that actually gets cancelled once you integrate this out and take into account the physics of the yellow chain. So maybe once that is cancelled, the next question is, in the limit as J becomes large, why is there some kind of a Gaussian theory? Because at the end you want a Gaussian theory to reproduce the physics of the asymptotic freedom. Yes. And that is still not completely clear. So it's I think a good question. We don't quite know the answer yet, I would say. Okay. But there are efforts to understand it better. Bhaskaran also had a question. Sure.
Shailesh, many years ago, while dealing with quantum spin liquid arising in spin half interacting systems on square lattice and so on, in the RVB theory, we did come across emergent U1 gauge fields, emergent fermions. It didn't cover the universe, but you know. Z2 gauge, there is, for example, along that line, there is an exactly solvable model due to Kitaev, where you have emergent Majorana fermions, massless Majorana fermion, and Z2 gauge field. So there are approximate theories where many
these things begin to happen. Yeah.
So this line of thinking was particularly taken up by Zhougang Wen. And he has done some, we can discuss about it.
I think I completely am with you. So many, I think experts in condensed matter physics will not find this completely new and they would be completely in agreement with this. I think the only difference, maybe in my opinion, between, after talking to some of my condensed matter colleagues, is that often in an asymptotically free theory, there are these scales which have, you've developed a mass gap, and often condensed matter theories will say, well, it's a gapped theory. But then what I'm trying to make perhaps a point is that near the quantum critical point, if you take this mass scale as the physical scale,
correct, yeah,
then you have a whole bunch of scales beyond that mass scale, all the way to the UV, which is also interesting.
Correct, yeah.
And so that gives you an interesting massive quantum field theory, and it'll be interesting to ask what type of massive quantum field theories we get. Are some of them asymptotically free and things like that? I think that's all.
Okay, we can discuss.
Yeah.
Thank you.
So my question was related. So is that the Hamiltonian you choose, that Hamiltonian, is that the interaction term have anything to do with the real system you are choosing? Like, so to deciding the Hamiltonian, so is that the interaction in the Hamiltonian will decide like what type of interaction you have to choose? So that may play an important role of deciding which type of Hamiltonian you choose.
Yes.
And another question of mine is like, so for this you choose 2 qubit to represent the infinite dimension. So you can like practically your aim is to do like finite dimensional thing, like infinite to finite. So in principle you can choose like 3 or 4 any qubit.
Sure.
But then the model will be different, right?
Yeah.
So how can you universalize thing, because we need a universal thing. So like.
Yeah. So that's the beauty of this Wilson's RG, is that as long as you preserve certain properties of symmetries and dimension and certain physics, right, the exact models don't really matter. There are lots of models which give you the same physics in the infrared. This was this, maybe I should explain it using the Wilson's RG perspective. Let me go back and, so maybe it's even before that, the first time.
Each point in the critical surface corresponds to different models.
Right, exactly. So, for example, if you think about what you would like to do is to, so this is like the space of all lattice models that you write down, right? So, for example, in your case, you'll say, if I start with just 2 qubits, maybe I'm here. If I start with 4 qubits, I'm completely in a different place, right? If I start with 20 qubits, I'm maybe here. I may be in completely different places in this whole space of models, right? But what Wilson says is that, well, if you do all of these things, at the end, there are certain properties of this fixed point. Certain directions are relevant and certain directions are irrelevant, it doesn't matter. So if you start with 2 different models, right, all I have to do is to tune this, and then close to this critical point, the long distance physics will be that QFT. If I do your 5 qubit model, it will be this, and then again the long distance physics is again the same quantum field theory. So that's why the details of what you do is not important. So now you might ask, does that mean there are many different qubit models that will create the same physics? Yeah, indeed, that is possible, right? What we are looking for is there a minimal one? And that will be an interesting thing to do, at least from quantum computation point of view.
Please use the mic.
Minimum?
Yeah, so there are some very interesting theorems from condensed matter theory that shows that a 1 qubit model will not produce the asymptotic freedom. So there are these no-go theorems that will say that 1 qubit is not sufficient. Exactly.
Can Qtreat do it?
Yeah, fair enough. You're completely right. So yeah, maybe I should be careful. So if the 1 qubit model also, you might be able to get it, but then You cannot have a nearest neighbor interaction, you just have to have something more complicated, and you may be able to get it. I still don't know that, but maybe we should think about that. I see. Okay, so it will be interesting to understand that. I don't, so condensed matter theorists have more intuition than me. But yeah, so there are certain, all I'm saying is that there are certain theorems, for example, with the one qubit model, there is something called the Leib-Schutz-Mathis theorem that says that there are only two phases in the theory. One is like a massless phase and one is like a dimerized phase. And the dimerized phase is not this phase apparently, and the massless phase is also not this phase. So I don't know if there is a critical point that will reproduce this physics. So that's my intuition about the one qubit model, but I will stand corrected if you can find a model that will reproduce this.
One qubit, three-dimensional maybe.
One qubit is a more interesting question. So we have recently studied a model where instead of doing the L equals 0 and L equals 1, we are trying to do the L equals 0 and L equals half. The L equals half doesn't even come from the original Hamiltonian. Remember, the original Hamiltonian only has 0, 1, 2, 3. So L equals half is somehow a new thing, right? But we said, let's try that out, what happens? So there with 0 and half, we haven't succeeded yet, but I can't guarantee that it doesn't exist. So that will be an interesting question.
Thank you.
Hello. So I have a question regarding this. Like, so you are telling like to look for the continuous QFT, you have to look at the fixed point of this RG flow. But usually it's like the CFT that lies on the fixed point, which has no scale. So if we want to look for QFTs which like mass scales, like how it fits in this step?
That's a very good question. So typically, if you sit right at that critical point, you're completely right. You get some kind of a CFT. But what I'm asking here is to do something slightly different. I'm saying there are relevant directions at that CFT, right?
Right.
So you add a small relevant perturbation to that CFT. That will create a mass scale in the problem because it's relevant, right? So then you ask, if you create a mass scale, that means at very, very long distances there is a scale that has been created. You make that scale physical, right? Say that is your physical mass. Then you ask, what type of physics exists all the way to the ultraviolet? And so sometimes you're completely right, the ultraviolet is governed by a CFT, right? But the infrared scale is governed by a massive theory, and that's exactly what happens, I claim, in this case. Let me show you that example here, right? So notice what happened in this case. There is a mass gap that is developed, but the ultraviolet, which is here, is actually scale invariant. It is going to this point, remember? So here what is happening is that the ultraviolet physics is governed by what we call the K equals 1 Vezumino-Witten CFT, and this is a perturbation about that. Actually it is not 1 equals 1, there are 2, remember it's a ladder connected by a coupling. So when you set that to 0, there are two decoupled CFTs and I'm coupling them together. So that's what is happening here. So the ultraviolet physics is governed by that CFT, right? But in the other case, in this case, the ultraviolet physics is actually governed by the Gaussian fixed point. So it is not a CFT that we think as some kind of an interesting interacting CFT. Here it is just a boring Gaussian fixed point with a small relevant perturbation, marginally relevant perturbation. That's what is happening.
Okay.
So it's just a perturbation about that particular
Fixed
point.
Okay, thanks.
Okay, so we already had 40 minutes of discussions. Thanks, Shailesh, for this wonderful talk again.